Yeah, we've been talking about stoichiometry here, and so we talked about basically two types of stoichiometry problems. I talked about really basic stoichiometry problems. And sort of basic stoichiometry problems are problems where really you're only given one piece of information about somebody in the reaction, maybe a reactant, maybe a product. And when you're only given really one piece of information, and in a sense can really only get to moles of one piece of information, that's sort of your basic stoichiometry problem. And really all stoichiometry problems kind of boil down to sort of the same 4 steps along the way. You want to make sure that you always have a balanced equation. As we talked about, nothing works correctly if you do not have a balanced equation. You'll have the wrong stoichiometry or have the wrong mole-to-mole relationships. Next thing that you typically want to do is whatever they gave you, you basically want to get it to grams, and then from grams, you want to really convert it to moles. And again, it is the molar mass from the periodic table that allows you to do that conversion. And really the reason why we got to obviously get it into moles is because we do use the mole-to-mole relationship from the equation. And that is really the third step, which is the mole-to-mole relationship. And really the reason we need to do that is because, again, we're given information about something we're really not interested in. And we really need a conversion factor to go from kind of what they gave us to what we are interested in the reaction. And where we get that conversion factor, instead of sort of looking it up in a table, is we use the actual equation as basically the conversion factor that allows us to do that. And it is nothing more than the coefficients from the balanced equation, which gives you that mole-to-mole relationship. And that obviously is why number 1 here is really important. You always got to start with that balanced equation. Again, otherwise it really does obviously throw off your calculations. The last step, again, here you should be in moles at this point, and you may have to convert to some other unit. And again, a lot of times that is grams that you're oftentimes asked for at the end. And once again, that is the molar mass that you can oftentimes use at the end of this calculation, not 100% of the time, but a lot of times you will kind of use the molar mass on the back end of the calculation. So those are really the 4 sort of basic steps to follow when you have a sort of simple stoichiometry problem, a basic stoichiometry problem. We then talked about limiting reagents. And the idea of limiting reagents, and really with that is what is referred to as excess reagent, or reactants. And the idea here is that in most reactions, both of the reactants, for example, are not used up at the same rate. There's always some reactant that gets used up first in a reaction, and that is the limiting reagent. So again, this guy gets used up first. This one you have, as we talked about, kind of plenty of, and you'll have some leftover of our excess reagent when the reaction is done. And in these type of problems, there are obviously a few different ways that we talked about that you could do it. You really can follow the same 4 steps as above, but you can insert here between these 2 steps a calculation to determine the limiting reagent. And that calculation basically is between the 2 reactants. And basically you're trying to determine, do you have enough of one reactant to completely use up the other reactant? So that's the basic sort of calculation that you can do at that point. And it is sort of mole-to-mole relationship between the 2 reactants. When you do that calculation, what you're figuring out, as I said, is how much of that other reactant you need to use up the first reactant. You would then compare your number that you need to how much you are starting with, which is what you should have after you do step number 2 there. And if you do have enough, then that substance would be the excess reagent. If you compare what you need to what you're starting with, and it is less than what you're starting with, then that would be your limiting reagent. So that is a way that you can determine that. Once you determine that, the importance of that is that it is always the limiting reagent that determines how much product that you make, because pretty much once it's gone, you cannot make any more product. So that's why it's always important to have to solve for the limiting reagent. The reason you kind of know that it is a limiting reagent problem is, and the way that you can recognize it is, if you are able to pretty much get to moles of each of the reactants, then it is a limiting reagent problem. So if the information given to you, you have enough information, whatever information that may be, that you're able to hit basically moles of each of those reactants, then you do need to do this sort of step. At that point, once you have the limiting reagent, you continue on with step 3 and 4, and you can then determine how much product that you would make. Another very common approach that we talked about as well, that a lot of people are taught, is you basically can just do 2 separate stoichiometry calculations with each of the starting amounts of the reactants, and the one that produces the least amount of product would be your limiting reagent and also your theoretical yield in that case. So that's a very popular way people are taught to sort of do it. We also touched upon and did a couple examples of more of an ice table approach, which is another method that you could do. And again, here, that's initial, that's change, and that's end in this case. And if we did have an equation such as this, we would start basically the first 2 steps just like normal. We're going to convert everybody into moles. We will have moles of this guy, we will have moles of this guy, and we could assume that we have none of our product to begin with. Remember that since this reaction is going from reactants to products, and we have no products to begin with, that we should expect over time that the amount of reactants should decrease and the amount of products should increase. And we represent that in the change part with the letter X and minuses and pluses. So because it is going to the right here, this would be minus 2x. And once again, as we talked about, the importance of including the coefficient here, what it is really doing is the mole-to-mole relationship, the stoichiometry of it. So if you don't include that number with the x in this version, you're not doing the correct mole-to-mole relationship, and you will get the wrong answer. This would be minus x, and then this would be plus 3x on the product side. You would bring pretty much everybody down here, and you basically will set your reactants equal to 0 and solve for x. And when you do solve for x, the smallest x value is your limiting reagent. And that would also be the moles of your limiting reagent, basically, are the moles, I would say, that of the change that's going to occur. And that x value, which one is the smallest? That is all the x's that we would find in this particular table. And again, sort of the benefit of this approach, as we saw in a couple examples, you could very quickly, within a couple of moves, pretty much answer any question that's going to be asked of you, how much of any product that you have, how much of the excess reagents left over, by just substituting that x back into the end part of it. You need to remember, obviously, that there's moles at that point when you do solve for it. And then obviously you can continue on using the molar mass to get the grams or something like that. So it's a very sort of, once you sort of practice it and use it, it's a very convenient way of doing limiting reagent problems, because again, you sort of have at your fingertips all the answers pretty quickly that you would need. Doing the other methods is perfectly fine as well. The only additional thing is, if you're asked something like how much of the excess reagents left over, you do have to maybe kind of start the calculation kind of from the beginning, or kind of cut it up again, and you must do some additional calculations. Any questions on any of that stuff there? We also finished up last night talking about yields, I think. We have our percent yield, which is our actual divided by our theoretical times 100%. And our actual yield is actually what we do get when we do the reaction. The theoretical yield is pretty much what you calculate based off of the equation and your starting amount. The theoretical yield is your maximum yield. That's like if everything went perfectly, that is what you should get out in that reaction. And then obviously the percent yield is basically the percentage of what you got to what you should have got. And again, a higher percent yield is what we want. And as we talked about, we don't want like over 100 yield, because that usually means, again, that you made some type of mistake. All right, so I think we laid up this example that I wrote all over right here. There you go. All right, so take a couple minutes. You should have worked on it at home. We won't hold our breath. All right, so work on it for a little bit here, and then we'll go over it. Titanium is 4788, I think. And this is the molar mass from the periodic table of each of those guys there. Okay, let's take a look, see how you're doing. So again, regardless of sort of what method you choose, as we talked about yesterday, I don't really care which method you choose, whichever one you're comfortable doing. Pretty much the first couple of steps are really the same. So we have an equation. It is balanced, unlike yesterday. Hopefully it's still balanced, I hope. The next thing that we want to do is convert each of these things into moles. We do know it's a limiting reagent problem, again, because we are given the starting amounts really of both reactants, and we have enough information to get to moles of both reactants. So that's really the key there. If you have enough information to get to moles, you know it's a limiting reagent type of problem rather than a basic stoichiometry problem. So in this case, they were nice enough to give us the molar mass of each of those things. If not, obviously you would go to the periodic table to do so. So we're going to use the molar mass that they gave us here to convert into moles. So that's a 189.7 grams per mole of our TiCl4. And I'll just get rid of some of this here, 2431. And we have 2431 grams per mole of magnesium here. All right, so converting these guys into moles, got some bigger numbers, but it really doesn't matter. It works the same way. You just want to make sure, obviously, you use your exponent button. So 2.46 to the 7 divided by 189.7. Looks like, keeping a scientific notation as might be a little bit easier. We'll go with 1.297 times 10 to the 5th moles of TiCl4, and 1.13 exponent button 7 divided by 2431. Gonna give us, not that, it's gonna give us 4.648 times 10 to the 5th moles of magnesium. So again, pretty much the same sort of opening steps here, regardless of what method you use. I am once again going to show you the ice table method again, so you can see it a few more times. And again, it is a calculation that you will do in 200B, so maybe it's good you learn some of it now here. All right, so remember initially here, we're going to take our moles that we just calculated there, and we're going to put it into our table. Bigger numbers here than usual, but 1.297 times 10 to the 5th. And for our magnesium, 4.648 times 10 to the 5th. And again, we're going to basically zero out our product side. Now, the change part of the table, again, really important because it does the stoichiometry for you and all that stuff. So our change here, we're going to go with minuses here on our reactant side. So that's going to be minus X because coefficient is 1. That's going to be minus 2X because coefficient is 2. This will now be pluses on the product side. Coefficient is 1, so it'll just be X and plus 2X here. Once again, the coefficient is 2. At equilibrium here, are not really the end here. We're going to bring everybody down. And again, I'm just going to get rid of the moles here so we don't have so much writing in between my numbers. And that would be X, and that would be 2X. Any questions on how to set up the table there? At this point, it's really, we're going to do the kind of short calculation here to figure out which one is the limiting reagent. We're going to set each of these guys equal to 0. So basically, this first guy becomes X is equal to 1.297 times 10 to the 5th moles. The second guy is basically 2X will equal our 4.648 times 10 to the 5th, basically divide by 2. And we will end up 4.648 to the 5th divided by 2. Going to give us a 2.32 times 10 to the 5th moles. Once again, here we are looking for the smallest number. And it looks like that guy right there is the smallest. So we do not need this guy. So this is our smallest. And that means that this is our limiting reagent in this case. And that should be our excess reagent, I believe, in this case. Questions on that so far? Now, remember, once we solve for the x, that pretty much is every single x value that we see in this table. And in this case, we're actually interested in TI, which is that guy. And from the table, we can see that at the end of this reaction, the moles of TI will equal X, which means it equals 1.297 times 10 to the 5th moles of TI. Using our molar mass from the periodic table, and we're going to multiply by it, which is 4788 grams per mole. And we'll take that times, take the right number, maybe it would be better, times 4788. Going to give us 6.21 times 10 to the 6 grams of TI. This is our calculation from the equation, which means that this is our theoretical yield. Any questions on that there? Now, ultimately, in this case, we are looking for the percent yield. So in this case here, our percent yield would be our actual divided by our theoretical times 100%. And in this problem, our actual 5.42 to the 6, I think. So that will give us 5.42 times 10 to the 6 grams, which was given in the problem as the actual yield, divided by our theoretical 6.21 times 10 to the 6 grams, times it by 100%. Let's see how we did here. 5.42 to the 6 divided by 6.21 to the 6 times 100. Going to give us about 87.28. 87.28% here yield. Not too bad, too shabby. Any questions on that? Now, we didn't have those other questions, asked to us, but if we want to know how much magnesium chloride, we could just take the X value times it by 2, and that would give us the moles of the magnesium chloride, and then times it by the molar mass of magnesium chloride, and that would give us the theoretical yield of magnesium chloride. If we want to know how much of our excess reagent would be left over, we could put our X value back into here, and that will give us the moles of the excess reagent that's left over, and we can use the molar mass of it to figure out how many grams would be left over. So once again, very quickly from getting the X value, you pretty much can get all those answers that you might be looking for in a particular problem. Any questions on that one there? Yeah. It was actually in the problem. I kind of erased it because I used the page, but it's right about there. It says basically that's how much is produced. And as we talked about, usually the actual yield is given to you in a book problem. So they'll somewhere in that problem tell you how much they produced of it. Obviously, in a lab situation, you would measure out how much you produced. Yeah. Other questions? All right, let's try another one here. I think you got. And I'll scroll this across. I think it might have the other approach in case you want to look at later on the recording. So. Hopefully they got about the same answer. I hope we get about 87-ish. That's good. All right. All right, so give this one a go. We've got 100 grams ammonia reacts with 100 grams of carbon dioxide, and we produce 120 grams of our product. Determine the percent yield here. Our normal guys here, carbon 12.01, nitrogen 14.01. What else we got there? Hydrogen 1.008, and oxygen 16 on the periodic table there. All right, see what you come up with here. Yeah, let's take a look at this one. So we have 100 grams of ammonia. We've got 100 grams of carbon dioxide. So once again, we have the grams of each of these starting reactants. That means we can definitely get the moles of each of those. So once again, that is going to tell us this is a limiting reagent type problem. Because of that, we're looking for the percent yield. This is the actual yield here of 120 grams. So ultimately, we're looking for our actual divided by our theoretical times 100% here. And in this case, we do need to calculate the theoretical. So again, we're going to start with the balanced equation. We're then going to convert everybody into moles here, I think. So we have 100 grams of each of those. So we'll start there. 100 grams of NH3. Using the molar mass from the periodic table, that's 1 nitrogen of 14 and about 3 there for hydrogens. It's about 1703 grams per mole of NH3. We also have 100 grams of CO2 in this case. Again, the molar mass from the periodic table, 1 carbon at 12 and about 32 there for the oxygen, gives us 4401 grams per mole for our CO2. So again, this is going to give us our starting amounts here of each of our reactants. And here we go. We got 100 divided by 1703, going to give us 5.872 moles of NH3. We have 100 divided by 4401 for our CO2, which is 2.272 moles of CO2. So once again here, if we take our equation, and we'll take our initial moles here. So this is going to be 5.872. This will be 2.272. And once again, here we're going to zero out our products to begin with. Reactions going to head to the product side. So our change here going to be minus 2x because of coefficient, minus x because coefficient is 1, plus x, and also plus x on that side. That means when we bring it down here for the end, we'll have 5.872 minus 2x, 2.272 minus x, x, and x. Any questions on the table here? So this is the part where we're going to determine the limiting reagent, and we're going to set each of our reactants equal to 0 and solve for x. So when we solve for x here, we see that for the first one, we basically just needed to divide it by 2. And that gets us 2.936 moles. Other one, basically, that is what x equals, 2.272 moles. So once again, the smallest will be our limiting reagent. So in this case, the limiting reagent CO2. The excess reagent here would be our NH3 in this case. Again, because that is the smallest value is what we're looking for here. Any questions on that there? Now that we do have our x value, once again, that x value is all the x values that we see in this table. That is this x, this x, this x, and that x. In this case, we are interested in the moles of our NH2,2CO, and that would mean that it does equal x, which means we would have 2.272 moles of this guy. And since we are looking for grams, we're going to get the molar mass of that guy. So that is 2 nitrogens at 1401 plus 4 hydrogens at 1.008 plus a 1201 for the carbon and a 16. If I hit the button right, 16, that's not going to work. Try that. 16. There we go. Looks like a 6006 on the molar mass there. And we actually want to multiply by 6006 grams per mole. And that will get us about 136.5 grams of our product here. And this would be our theoretical yield for that product, which is what we need for our percent yield. So our percent yield here would be the actual, which was given to us, and I believe that was a 120, if I'm not mistaken, divided by our theoretical, which is 136.5, times it by 100%. And we get a 120 divided by 136.5, times it by 100. We're going to end up with 87.91%. Still not too bad in that sense. Any questions on any of those steps there? Now, again, it wasn't asked here, but if we did want something like to know how much water we would have produced, we could just go back to our table, and the moles of water in this case would also equal X, which means we would have 2.272 moles of water would also be produced. And if we use the molar mass of water, which is 18.02 grams per mole, we can just as quickly really figure out how many moles of our water we would have made. And in this case, it would have been about 40.94 grams of water would have been produced, and that would have been our theoretical yield for water. And in this case, our excess reagent was this guy. And we could go back and also figure out how much of that excess reagent. So 5.872 minus 2 times our X value of 2.272 moles tells us that at the end of this experiment, we will have about 1.328 moles of our NH3 left over, which we could also multiply by the molar mass that we had earlier. And that would tell us that at the end of this experiment, we would have about 2262 grams of it left over. And we started with 100 grams, right? So you can see not very long there. I was pretty much able to calculate everything that Chem might ever be asked for without having to maybe start from the very beginning and stuff like that. You know? Any questions on stoichiometry, limiting reagents, percent yield, how to calculate any of those things? Okay, then let us continue on here. We're going to talk a little bit about solutions next, and we're going to relate it into some solution stoichiometry as well, which really works kind of the same way. So let's go through this here. And again, I'll scroll this on the screen in case you want to look at it later. This is, again, the opposite or another approach that you can take the same problem we just did as well. And looks like they got the same answer. So again, that's good. All right. All right. So let's talk a little bit about solutions. And that's going to lead us to some solution stoichiometry. So a solution is a homogeneous mixture of 2 or more substances. Solutions are the ones that get the aqueous symbol next to it. And there's really 2 parts to a solution. The solute is the smaller part of the solution. The solute is typically the stuff that's dissolved in the larger part of the solution, which is known as the solvent. So if you take the solute and the solvent together, you make a solution. So for example, if you took something like sodium chloride, salt basically, and you take water, both of those things are pure substances. But when we put them together, it makes a mixture, right? So 2 things coming together there, and it does make a mixture. The sodium chloride will dissolve in the water, and it will make a sodium chloride solution that will get that aqueous symbol next to it, right? As we know from our solubility rules, sodium soluble in everything. So it always will make a solution in this case. How do you know what the solute is in a solution? It's pretty simple. It is the name of the solution. So if you have a sodium chloride solution, it is sodium chloride is your solute. If you have a hydrochloric acid solution, hydrochloric acid is your solute. Potassium nitrate is your solute. So pretty much the name of the solution is the solute. And I would say in most cases for ionic compounds, water's a lot of times your solvent, but water doesn't always have to be your solvent. It can be other things, and for certain things, water is not a great solvent. But for a lot of ionic compounds, polar things, water is a really good solvent for it. Here's a few different examples. Sometimes we do think of solutions as kind of being in liquid state, but technically speaking, you can have a solution as a liquid, a gas, or a solid, as we can see in these examples. For example, our soft drinks, mostly water, right? But made up of sugar, CO2, and whatever other syrup and stuff I guess they put in that particular drink. Air is a solution in a sense. It's a mixture of a bunch of things, and in most cases it does look homogeneous, right? Depending on where you're at, I suppose. But also the major component of air, as you may know or may not know, is nitrogen, not oxygen. So nitrogen is actually the major component of air, followed by oxygen, and then other gases depending on what air you are breathing currently at that point. Solder, there is some lead and tin together, so some mixtures of those type of things. So although we do oftentimes think about solutions as being sort of in the liquid state and being aqueous, and in most cases that's pretty much what we come across it in chemistry. The technically can be some other states as well. So that brings us to concentration of solutions, and really the major sort of most used concentration of a solution is molarity, and molarity is moles per liter. It really is moles of solute per liter solution. You could think of molarity, which is abbreviated with a big M, as being moles per liter. You could think of it as a formula, because frankly, we use it to solve for any of those three things. So in certain situations, we solve for the molarity. Other situations, we solve for the moles or the liters. So we do actually kind of solve for all three of those things. So it's kind of very similar to like density, where you can solve for any of those three things in sort of the density formula. If we are going to solve for moles, it would be liters times molarity, and that is a very common calculation that we do a lot. If we want to solve for liters, that would be moles divided by molarity. When you are using molarity by itself, sort of standalone molarity, and doing a calculation with it, the volume needs to be in liters. Yeah, so it does need to be in liters for it to cancel out correctly the way you're probably thinking about it. That also means that this conversion we use a lot, right? 1000 milliliters is a liter. So that is something that we do a lot when we're using molarity and volume together. Now, if you do multiply molarity times milliliters, which sometimes people do quickly, times it by molarity, you do not get moles. You get what is known as millimoles. Kind of like moles, but a little bit smaller. Yeah, so it's like millimoles, which is all good. If you're kind of going to divide by milliliters, you'll get the molarity back in that sense. Because if you take millimoles and you divide it by milliliters, the millis cancel, and you get moles per liter, which is back to molarity. I would say probably 99% of the time you should be sure it is in liters, because the rest of your calculation probably depends on it being in moles and not millimoles, so you don't screw up and be off by a factor of 1,000. But technically speaking, you can multiply it by milliliters, but you do not get moles. So there is that factor of 1,000. If you're not careful, you might mess up on it. You don't want to do that. So again, make sure it is in liters pretty much most of the time when you're using molarity by itself. Now, when we look at a solution that is 4.50 molar, say sodium chloride, what that means is you should also really get rid of the big M. And the reason you should get rid of the big M when you do the calculation and then use both of the units of moles per liter is because most people, when they leave the big M, all they think about is moles and have no idea where the liters is or the volume part is, and they forget all about it. So this is the same as saying you have 4.50 moles of sodium chloride in 1 liter of solution. And that is what molarity is. The number stays with the moles part. It is 1 liter. You could use this like a conversion factor and sort of do problems with dimensional analysis where you could see the units cancel out. So you could technically, if you wanted to use this as like a conversion factor, flip it around and do the moles on the bottom, liters on top. but I definitely and highly recommend that you get rid of that big M and kind of invert there the moles per liter unit, because I can't tell you how many people I've seen just kind of forget all about the liters, don't know where it's at. Now, when we talk about molarity and molarity of ions, there is a relationship. So if I did have something like a 4.5 molar solution of sodium chloride, when sodium chloride breaks apart, it is a strong electrolyte, which means it breaks apart into a sodium ion and a chloride ion. And if this molarity was 4.5 molar, the molarity of the sodium ions by itself, if you're just interested in the sodium ions, is also 4.50 molar, because it is a 1-to-1 relationship between the entire thing and just that ion. If you wanted the concentration of just the chloride, it also is a 1-to-1 in this case, which means the molarity of the chloride ions that are floating around in that solution would also be 4.5 molar. It is not additive. Obviously, 4.5 and 4.5 doesn't equal 4.5, but that's basically how it breaks apart in solution. The reason for that is here, if you had something like here. So if you had, say, exact same molarity, we'll go with 4.50 molar calcium chloride solution. When calcium chloride breaks apart, you get a calcium ion and 2 chloride ions. So if this is 4.50 molar, it is a 1-to-1 relationship there between the calcium and the whole thing, which means that the concentration of calcium ions would be 4.5 molar. When we look at the chloride ions, in this case, it is a 1-to-2 relationship between the chloride ions and the whole thing. You would need to multiply the molarity by 2, because you get like twice as much chloride for every 1 calcium that goes for a swim, which means the concentration of the chloride ions in this case would be 9 molar. So if it does break apart into multiple ions, you do need to basically multiply by the coefficient of how many you get, because again, for every 1 of those calcium chlorides that go for a swim, you get twice as much chloride floating around, so it's twice as concentrated in terms of the chloride ions. So sometimes you are asked about just the individual ions. That is the short version of doing that calculation, just to show you sort of the long version of it and really how we get to that sort of relationship. It actually is like a stoichiometry relationship of how we get there. So if we did our calcium chloride here, we would have 4.50 moles of calcium chloride per liter. It is just like in stoichiometry here, a 1-to-1 relationship between our calcium. So 1 mole of the entire thing gives us 1 mole of our calcium. The moles in the entire thing cancel, and we end up with 4.5 moles per liter of our calcium ions. We do the same thing for our chloride ions in this case. It is a 1-to-2 relationship. So for every 1 mole of the entire thing, we get 2 moles of the chloride ions. The moles of the entire thing cancel. We end up with 9 moles per liter of chloride. So that's basically why we multiply by 1 on the first guy, multiply by 2 on the second guy. So that's sort of the quicker way of doing it. Just take the coefficient there and multiply it by the concentration. Obviously, on the bottom one, everybody would be a 1-to-1 relationship. Any questions on how molarity relates to individual ions? Okay, so let's take a look at an example now that I scribbled all over this page here. I think. All right, so why don't you give this one a go? What is the mass? So how many grams? grams here of Ki is required to make 500 milliliters of a 2.8 molar Ki solution. Potassium there is 3910. Iodine is 126. Okay, so let's take a look. So we are looking for the mass here. And again, we're obviously dealing with molarity, which is our moles per liter. And if you're not sure where you should start, you can sort of mark off what's given to you. So in this case, we do have 500 milliliters, although it's not liters at this point, it is like a volume. And obviously we have the molarity here. So obviously here it would make sense to solve for moles, which then we could obviously use the molar mass to go from moles to grams to end up with what we need. So here we will start off for moles, which again is a very common calculation. It is liters times molarity. And once again, we do want to make sure that we are in liters. So we do need to convert this guy out to liters. So that's going to be 500 milliliters. Once again, there's 1,000 milliliters in a liter. You can move the decimal place 3 places to the left as well if you want to do that. And that will give us 0.5 liters. Also, as I mentioned before, I'm going to get rid of the big M and turn it into really a conversion factor, and that would be 2.8 moles per liter. Or again, if you're going to do some dimensional analysis, you could really, if you needed to, kind of flip the molarity around. But once again, the benefit of this is you could hopefully see the liters part there in the volume part of it when you do the calculation. So if we take more of a dimensional analysis approach, which is a good approach here, so you don't miss anything, we'll have our 0.5 liters. Once again, we're going opposites to cancel, which means we do actually need that guy just like that. 2.8 moles per liter of Ki. And if you did get an answer at this point, you would end up with 1.4 moles of Ki. That's close to what I want, but obviously I want grams, so I do need the molar mass of Ki. So pretty much we just need to add these guys together, I think. So we'll just add those guys together, and we will end up with 3910 plus 126.9. 166 looks like. And we will then use that to get to grams, 166 grams per mole. The moles will cancel, and that's going to get us about 232 grams of Ki is needed. Obviously, you could do it all in one calculation without the number in the middle if you wanted to do so. Any questions on that there? So that, yeah. Yeah, so in this case, it looks like everything has 3 sig figs, so we just multiply and divided, so 3 would be the right one. Yep. Other questions? So what this number really does represent is if I wanted to make the solution, I should measure out 232 grams of the Ki, right? Dissolve it in enough water to make a total volume of 500 milliliters. Give it a mixy, shaky, maybe not so much shaky, but you will get it all to dissolve, and then you should have a solution that has a molarity of 2.8 molar in that case. Any questions on that there? All right, let's try another one here, I think. Do it on this page here. We'll steal this page, I think. All right, what is the molarity of a solution made by dissolving, let's go with 132 grams of sodium nitrate and enough water to make 355 milliliters of solution. All right, and again here, sodium 2299 grams per mole, nitrogen 1401, and oxygen 16. I'll do it as well since I just made up. Okay, let's take a look. So once again, we're looking for molarity, which is moles per liter. In this case, we have grams given to us, which is not moles, but we definitely could get to moles using the molar mass. We have milliliters, which is not liters, but we could definitely get to liters by doing a conversion. So we really just need to do a couple conversions and then pop it into our equation here. So we'll start with the grams to moles. So we'll add this up. It looks like we have 3 of those. So I think it's 85 grams per mole here when you do that. So we will end up taking 132 grams of sodium nitrate. We'll use the molar mass from the periodic table, which is our 85 grams per mole. And that's going to give us 132 divided by 85. Looks like maybe like a 1.5529 moles here. Our milliliters, once again, does need to be converted into liters, and you can either move the decimal point or obviously here divide by 1,000. 0.355 liters. So now we do have both of these guys in the proper units to calculate the molarity. So our molarity here would be 1.5529 moles over 0.355 liters. And it looks like maybe a 4.37. Now the units do not cancel, so the moles stay with the number, and it is per 1 liter of sodium nitrate, or you can at the end there bring the big M back if you like, and obviously give it either way there would be okay. Any questions on molarity or how to calculate molarity? It is obviously something that we use a lot in solution stoichiometry, and titration is coming up next week. So it's important. All right, then let's talk about another aspect of a solution. So oftentimes we are given solutions that are really more concentrated than we want to use them. So a lot of times the process of dilution is used to basically make a more concentrated solution less concentrated. There we go. Oh, by the way, this you could use to prepare a solution, by the way. Although you can't really see it on the screen, but maybe on your notes you can see there is a flask there, and there's like a flask like right here-ish. There we go. No, it came to life there. All right. So this is what's referred to as a volumetric flask, and volumetric means expensive, also means there's just one marking on it, and that marking represents the volume, and that line right there represents the volume of this. So if this was 100 milliliter volumetric flask, that would represent 100 milliliters. And usually with volumetric glassware, you do go to 2 decimal places. So you usually take 100.00. So you take a little bit of your salt, a little bit of water. You typically would want to kind of not fill it to the neck of the volumetric flask, which is good practice for next week when we do that experiment, so you're not dumping out your solution. So usually want to kind of keep the level halfway here and try to get this solid to dissolve. You may add a little bit more water as you are getting it to dissolve, and eventually, hopefully you get it all dissolved. At that point, you typically want to keep it underneath the neck of the flask until it's all dissolved. And then you should carefully, with like a wash bottle or something like that, fill the rest up to the line. And that line and that meniscus obviously should be at the line here. As we look at it, and put the cap on and really sort of mix it at that point to get your solution that is properly volumed, if you will. It's a very accurate way to and precise way to measure out a solution. Now, if I did this per se, and maybe I wasn't very careful and I changed the slide, and still wasn't very careful, and I just filled the water up past the line, can I just dump out the liquid to the line? I cannot, because frankly, there goes some of your solute that you dissolve. So next week, make sure you don't go over the line. Yes, go very slow until you get to the line, so you don't have to do that. Because when you do that, obviously you would dump out some of your solute that's dissolved in the solution. So we'll use that next week. But talking about dilution, as I mentioned before, when we have solutions that are really more concentrated, they're sometimes referred to as stock solutions, and we want to use them in a more dilute sort of fashion. We do the process of dilution, and dilution really lowers the molarity of that solution. And really, the reason for it is, if you think about what molarity really is, which is moles of solute over liters of solution. When you do a dilution, the only thing that you add is more solvent, and a lot of times more water in that case. And that means that the moles of the solute before and after the dilution is the same. The only thing that you added is more solvent. And if we look at what molarity really is, the top is solute, so you're not adding any more of that. You're adding more solvent, which means you're actually increasing the bottom number here in the molarity equation, which means the bottom number gets larger, the molarity gets smaller. So the molarity comes down. So when you look at a concentration unit of molarity and it's a big number, like we had some, I think the other week, maybe like 18 molar, 16 molar. Yeah, that's like, very strong stuff. Yeah. Smaller molarity number, more dilute, not as strong. There is a molarity dilution equation, and this is M1 V1 equals M2 V2. And this is like before the dilution usually. The more concentrated stuff, this is after the dilution, the more dilute stuff. So M1 is typically the molarity of your more concentrated solution. V1 is typically the volume of that concentrated solution you need to make the solution you're looking to make. M2 is the concentration of your dilute solution, and V2 is concentration or the volume of your dilute solution that you want to make. This is one of the equations where it is okay to leave the volume in milliliters, and that is because unit-wise, if we did an M1 V1 equals M2 V2 situation and we wanted to solve for M2 would be M1 V1 over V2 in this case. Now, if we did this in molarity times milliliters divided by milliliters, the milliliters cancel and you're back to molarity. So it does work out okay if you want to do it with milliliters here. And this should be the only place that you do it with milliliters. Again, if you're doing just a non-dilution calculation with molarity, make sure it's in liters so you don't mess up your calculation, but you can leave it here, or you can convert it to liters. It's all good. You can do that as well. Now, I would say most people, when they do a dilution equation, that is the equation they use. Some people will be taught C1 V1 equals C2 V2, where C is just a generic term for concentration. So although most of the time concentration is in the units of molarity, you technically use any unit of concentration in this equation. So you can use percent mass to mass, percent mass to volume, volume percent, whatever it may be, and it will work the same. But most of the time, your concentration units are going to be probably in molarity, and that M1 V1 equals M2 V2. I would highly caution you, as we'll talk about shortly, you should not use this equation in every situation where you have molarity and volume, and you should probably not use it when you're doing stoichiometry involving solutions. People want to do it, and they end up with the wrong answer because they'll have the wrong mole to mole relationship. Sometimes you'll end up with the right answer because it's a one-to-one relationship, so you get lucky. But if the relationship in a stoichiometry problems we'll talk about is not a one-to-one, you will get the wrong answer. So you should not use this for titration problems or solution stoichiometry problems, although sometimes online you'll see this labeled as the titration equation, and it's really not. It is a titration equation for a one-to-one relationship. Other than that, you're not going to get the right answer if you sort of use it. So strictly only use this for dilutions and you'll be in good shape. So as you can see here, the only thing that changes, if we count in circles perhaps, is the volume of the solvent, and the solution changes. When a solution reacts and a reaction takes place, what is reacting, the solute or the solvent? It is actually the solute. Yeah, so it's actually the stuff that's dissolved in there. It's actually doing whatever reaction that you do, like when you do a precipitation reaction, whatever it may be. It's really what's floating around in the solution, that solute, that actually goes through the reaction and reacts. And that is why when you have a more concentrated solution, you have a much higher concentration of solute, which means it's going to react pretty good. Yeah. But if you get a more dilute solution where you have, say, mainly water or solvent, you have very little, say, solute dissolved in there, it may not react as well as something that's more concentrated. So it is always the solute that was reacting when we do have a solution.